So hello friends, welcome back to another video. In this video we will discuss about pass transistors. So what are pass transistors? Until now, like we have seen implementation of logic gates and also other Boolean functions using CMOS logic family, right? So CMOS logic family basically uses like more number of transistors when compared to pass transistor. That means we have another type of modeling where I can design all the logic gates as well as the Boolean functions using lesser number of gates. Okay, so what is the logic in the pass transistors is like you have an NMOS and a PMOS. By using only NMOS and PMOS we will be designing the logic gates or the other Boolean functions. Okay, so pass transistor is nothing but it is a switch. Okay, it is an unidirectional switch in which like for suppose if I have the input A here and X and Y. Okay, so Y will be equal to X only when A is equals to 1 for an NMOS. Okay, because this is an NMOS transistor. Okay, Y will be is equals to X. That means output will be equal to input only when A is equals to 1. Until and unless I give the output input here A equal to 1, X will not be equal to Y. That means it is acting as a switch. Okay, it is acting as a switch. Okay, similarly if I have a PMOS, right, same condition A, X and Y, Y will be equal to X only, Y will be equal to X only when A is equals to 0, because when the input is equals to 0 my PMOS will be equal to on, right. So by using this two basic understandings we can design any gate by using pass transistors. Okay, so and also the beauty of pass transistors is only by a simple structure. Okay, by using two gates we can construct any logic gate. Okay, see for suppose if I talk about AND gate. Okay, if I talk about AND gate. Okay, for suppose if I take the same thing by using CMOS logic family, it requires 6 gates, gates by CMOS logic family. 6 gates are required to implement this AND gate by using CMOS logic family. Okay, how the structure looks like I have PMOS transistors connected in series, connected in parallel, and NMOS transistor in series for an AND gate, and also at the output of the NAND gate you give an inverter connection, CMOS inverter, so that it becomes an AND gate. Okay, so 3 PMOS transistors, 3 NMOS transistors. But by using pass transistors only 2 gates are required to design the logic. Okay, how to design the logic is I have a simple structure. Okay, I have a simple structure like this, one PMOS and one NMOS. Here I will be getting the output, and here I will be using one of the inputs. For suppose if I take the truth table of the AND gate, A, B and Y, 0 0 0 1 1 0 and 1 1, right. This is 0 0 0 1, right. So what I will do is I will split the truth table, okay, into 2 parts, and I will give one of the input here. Okay, one of the input A as here, and I will operate with respect to the other input to the output. Okay, that means here if you see, for A is equals to 0, whenever A is equals to 0, this particular transistor, so PMOS will be on. For A is equals to 0, PMOS equal to on. Okay, that means for two conditions this transistor will be on, and for the next two condition A is equals to 1, this NMOS transistor will be on. Okay, so when PMOS transistor is on, NMOS transistor will be off. That means the output will go from this transistor to the output when A is equals to 0. Similarly, when A is equals to 1, the output goes from this transistor to the output. Okay, so by this understanding, let us try to draw an AND gate. Okay, so you see the structure. So for my convenience, I will take PMOS in the above, you can take it, and NMOS in the below. Okay, and I will take one of the input here, A. Okay, my truth table goes like this: A, B, Y, 0, 0, 0, 1, 1, 0 and 1, 1, 0, 0, 1. Okay, the beauty of pass transistors is this particular structure is same for all the logic gates. Okay, only thing varies is what is here and what is given here. Okay, if you can understand what it should be given, all the logic gates right from AND gate, OR gate, NAND, NOR, exclusive OR and XNOR gates, all the gates can be designed by using simple by this structure, right? So see here again, I told like I will be splitting the truth table here. Okay, so when A is equals to 0, this particular transistor will be on. Now compare B and Y. Okay, B and Y, right? So when B is equals to 0, also my output is 0, and when B is equals to 1, also my output is always equal to 0. That means I will be connecting and ground here. Okay, and ground, right? Such that when A is equals to 0, my output, this transistor is on and the output is always equal to 0. Okay, now when A is equals to 1, this particular transistor will be on, right? So you see here, when A is equals to 1, if B is equals to 0, Y is equals to 0. If B is equals to 1, Y is equals to 1. That means my output Y is nothing but it's a B. Okay, so you can see this is how an AND gate is realized in pass transistor. Okay, so what is the difference between CMOS implementation and this implementation is nothing but in CMOS we have separate VDD and VSS, that means ground, right? Here in pass transistors there is no VDD or VSS. Okay, no separate VDD or VSS is given. Okay, only by using the inputs, only by making use of inputs. Okay, and only by making of the inputs, we will be constructing or implementing the logic gates here. Okay, so this is the implementation of an AND gate. Similarly, I can implement, let us take OR gate. Okay, OR gate. Like I told you, the structure is same for all the logic gates. For all the logic gates, the structure is same. Only thing changes is the what input you are giving at the, this is my Y and this is A. Okay, so A, B, Y. 0, 0, 0, 1, 1, 0 and 1, 1, right? For OR gate it is 0, 1, 1, right? Correct? Okay. So see, and also please remember why we are taking A input here, because in my truth table it is convenient for me to use when A is equals to 0 and when A is equals to 1 case. Okay. No, if I wanted to take as a B input here, yes, you can take that particular input also as B. Okay, you can operate with respect to B also. Okay, you take it B here and that means like when B is equals to 0, you check the A input and the Y output. Okay, that also can be done, right? So but for our convenience, it is simple for me to just divide the truth table into two parts, when A is equals to 0 and A is equals to 1. Okay, so the OR gate goes like this. So what is the case? So when A is equals to 0, you can check here B and Y are same. Therefore, when A is equals to 0, this particular transistor PMOS will be on. So Y is nothing but Y is equals to B. Okay. So when A is equals to 1, you check this one. Even if B is equals to 0, Y is equal to 1. Even if B is equals to 1, the Y is always equal to 1. So what I will do is I will connect a plus 5 volts here, right? Such that my output Y is implementing an OR gate. Okay. Similarly, I can have a NAND gate. Okay. So what is the construction? The construction goes like this. The same connections here. This is Y, this is A. What is the truth table of NAND gate? A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1, right? So NAND gate means 1, 0, 0, no, 1, 1, 0, 1, 1, 0, okay. So you can see here what will be my input here. When A is equals to 0, my output is always equal to 1, so I will be connecting a plus 5 volts here, and when A is equals to 1, when B equal to 0, Y is equals to 1, when B equal to 1, Y is equals to 0, that means it is nothing but complement of B, that is B bar. So I will be giving an B bar input here, such that my structure, my pass transistor structure circuit diagram is implementing an NAND gate. Similarly, let us take NOR gate. NOR gate. Okay. So the structure goes like this. I have the same circuit diagram here. This is my Y and this is my A. So A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. Okay. For a NOR gate, it is 1, 0, 0, 0, 1, 0, 0, correct. Next, so you can see here what will be the output Y. Y is nothing but, you see here, when A is equals to 0, when A is equals to 0, Y is nothing but B bar, and when A is equals to 1, Y is nothing but always a 0. So I will connect an ground here. Okay. Next, we will talk about exclusive OR gate. Okay, again I am having the same structure. This is Y, this is A. What is my truth table? A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. So what is exclusive OR? I get output 1 whenever there are odd number of 1s in my inputs, right? So what will be the diagram here? So again, if I divide, when A is equals to 0, Y is nothing but equal to B, and when A is equals to 1, Y is nothing but it is B bar. This is the implementation of exclusive OR gate by using pass transistors. Similarly, I can have exclusive NOR gate. Exclusive NOR gate. So I will draw the same structure. Remember, the structure is same for all the logic gates, only the inputs you are changing, right? Until here it is same, Y, A, B, Y, 0, 0, 0, 1, 1, 0 and 1, 1, right? What is an exclusive NOR gate? It is 1, 0, 0, 1, right? One, 0, 0, 1. Okay. So what is the input here? When A is equals to 0, Y is nothing but B bar, and when A is equals to 1, Y is nothing but it is B. Okay. So this is the simple construction of the logic gates by using pass transistors, right? So it is very much compact, only similar kind of, only we are using two logic gates to implement all the gates. Okay, two transistors, we are only using two transistors, one PMOS and one NMOS transistor to implement all the logic gates. So it is a simpler structure. Okay, and also it is less costlier when compared to CMOS logic family. It is faster when compared to CMOS logic family. Pass transistors are faster, and also these are compact, less costlier, right? So I also speed is more, right? So there is one disadvantage with the pass transistors. It is we have degraded output. Degraded output. This is the limitation of the pass transistors. Okay, what do you mean by degraded output? Degraded output is nothing but, like, I am not using any separate VDD or VSS for the design in the pass transistors. Only I am making use of the inputs to design the logic gates and all. So I may not get an perfect output because my inputs A and B will be always continuously changing from 0 to 1 and 1 to 0. So my output is degraded output. That means I don't get a strong 1 or a strong 0 at the output. So that is the limitation of the pass transistors. Okay. So in the next lecture we'll be looking at the other multiplexer design as well as decoder design, comparator design, half adder, full adder design by using pass transistors. Okay. And fine, if you understood the concept of pass transistors, please like the video, share and subscribe the channel. Thank you for watching. Thank you.